This is my homemade electric bike. It isn't powered by a hub motor or add-on kit, but instead powered by a large drone motor. It's taken me 3 years to get to this point, and I want to share what it took to build an electric bike from scratch. So grab a drink, sit back, and let's rewind 3 years. At the time, I was studying at university, and my housemate Danny built an electric skateboard using these hobby-grade brushless motors, combined with speed controllers designed for radio-controlled cars. Now, I personally prefer 2 larger wheels over 4 small wheels, and wondered if this setup could be modified for a bike. So I purchased a cheap bike from Amazon with a large motor that could be attached to the rear of the frame using a 3D printed mount. This motor would then drive the rear wheel via a belt and pulley system, where the large rear pulley was also 3D printed and cable tied to the wheel spokes. This drivetrain worked well, but the cheap speed controller had a slight issue. The throttle input controlled the speed of the motor and not the power output, which makes sense as it is called a speed controller. But the issue is that it will do anything to maintain the speed input you give it. So when climbing a hill, if the motor can't maintain the speed that you want it to, the speed controller will dump a load of current into the coils and toast the motor a little. After this, I didn't want to spend too much money on a project that might not work, but I also didn't want to risk using the same speed controller and burn out another motor. So I purchased a VESC, or VESC. This speed controller was twice the price of the previous one, but it had current limiting capabilities, meaning the motor would essentially never burn out if I set the limit correctly. Also, I didn't want to buy another motor and therefore ended up rewinding the motor by hand, which is why the coils in the original electric bike video look different to the original motor coils. And it was this rewound motor and VESC setup that powered the bike in my first electric bike video, back in 2017. But there were some fundamental flaws with the design. The first being the pulley ratio was far too high, meaning the acceleration wasn't great. On the plus side, it had a top speed of 34 miles per hour. I then 3D printed a new larger pulley which produced more torque at the rear wheel. But this would also reduce the top speed. And this began my quest for more power, so I built this ridiculous setup. Yep, that's 2 motors attached to a bag rack above the rear wheel. These 2 motors were linked together via a single belt to drive the rear wheel, but it never rode more than a couple hundred meters due to an unforeseen issue. As this motor applied torque to the belt, it would increase the tension here, but also decrease the tension here, meaning the reduced tension around the second pulley caused the belt to skip, rendering the second motor useless. I then made this mount where there was only one output pulley driving the main belt, and a secondary smaller belt connecting the 2 motors. This setup worked surprisingly well and had lots of power. But the biggest problem with this setup was not being able to tension the smaller belt joining the 2 motors together, as the outer case of the motors would spin. Also, shortly afterwards, one of the 2 speed controllers died. Fortunately, I was contacted by a company called Tramperboards, who are working with Benjamin Vedder on a new speed controller, called the VESC 6. This new speed controller could handle a lot more current, meaning I could use one large single motor rather than 2 smaller motors, and get a similar power output. I also invested in some lithium-ion cells to build a 44 volt, 15 amp hour battery pack, and built a part 3D printed, part aluminium motor mount, which was pretty similar to the version 1 electric bike, but with around 3 times the power. It also had regenerative braking, which was controlled by a thumb lever on my left handlebar. Regen charging coming up to this. But after lots of testing, it only increased the range by about 3.5%. And get the power on. Oh yeah, it's got plenty of torque. I ran this same setup for the following 8 months and rode around 1,500 miles with minimal issues, other than replacing the belt once. In fact, I ended up replacing the tyres and brake pads more often, which led me to eventually upgrade the bike, which required a whole new motor mount design. And to do this, I imported photos from multiple camera angles into my CAD software to produce a 3D model of the bike, and designed this bracket where the motor could be mounted behind the seat post, and cut a prototype from plywood. Then came the difficult part of designing the rear pulley, as there was very little space between the wheel spokes and the brake caliper. The plan was to mount the pulley to the brake disc, as this was a pretty solid mounting point, and then bend some aluminium arms to an angle where they would just miss the brake caliper, which was a very tight fit but worked nonetheless. Then with a total of 6 spokes and a 3D printed tooth pulley, it was time to work on the motor mount again, which I realised needed a full redesign as I wasn't comfortable with this long arm potentially twisting into the rear wheel. This new design utilised the water bottle mounting bolts and a clamp round the seat post at the rear, which kept the motor protected inside of the frame. But there was a problem: the pedals hit the motor, so I cut the end off. And also mounted the belts and pulleys, which, as you can see, there are 2 belts instead of just 1. This is to gain a larger pulley ratio between the motor and rear wheel, where this belt produces a 2:1 step down and the larger belt produces a 37:4 step down, meaning a total motor to wheel ratio of 37:2, or 18.5:1, but don't tell my math teacher. This produced so much torque at the rear wheel that the pulley exploded instantly upon testing, due to a weak design. So I beefed up the spoke mounting holes and it held up a lot better. But then I was having motor issues. It seemed it wasn't possible to run the motor so close to the aluminium mount. And yes, aluminium isn't magnetic. But if I drop this magnet down this aluminium tube, you can see there is clearly some resistance. I won't go into detail how it works, but it was causing so much resistance on the motor that the motor lost sync with the speed controller and for a short period tried spinning the wrong way, causing the belt to skip and make that horrible noise. So I had to widen the slot a little. Also, the shaft was slipping in the motor due to my genius idea of cutting the end off, so I had to make this plate to hold it in place. I then 3D printed a cover for the motor and the bike was ready for a test ride. And this was the last electric bike video I uploaded to YouTube. But a lot has changed since then. The dual pulley setup produced a lot of noise and resistance, which reduced the efficiency and range. So I flipped the motor around and made a new mount which connected the motor output directly to the main drive belt, and completely redesigned the large rear pulley to be manufactured from a single piece of aluminium, which removed the need for the singular spokes, and was spaced away from the brake using a few aluminium discs. I also programmed an Arduino board to gather serial data from the speed controller and display all the important information on an LCD screen. If you own a VESC 6 and want to make a similar display, I'll post a link in the description for more info. And this was the final design for the next year and a half, when I decided to upgrade the motor. The diameter of this new motor is 25% larger than the previous motor, and it's got 42 magnets instead of 14, which I had no idea if it would improve the performance, but it was worth a try. The only problem is this motor lacked an output shaft long enough to mount a pulley, as it's designed for mounting propellers to. So I had to make my own shaft which would bolt to the motor housing, pass through all the bearings and attach to a pulley, like so. This could then be bolted to the new aluminium motor mount, with the other mount plate being cut from 3mm carbon fibre to avoid the magnetic motor issues again. And this fit nicely inside of the frame, but upon testing there was a noticeable vibration coming from the motor. This was due to my amateur lathe turning skills, where I'd machined the shaft slightly too small and there was play in the bearings. So this is my workaround. A 12mm shoulder bolt. These bolts have a shaft section which is machined perfectly to fit within bearings, but to turn it into a usable motor shaft, I filed down the head to lock into an aluminium bracket that I cut on my CNC router. I then sprayed it black and bolted it to the motor, and also cut the threaded section off. Then all I had to do was replace the bearings in the motor for 12mm inside diameter rather than 15mm, and now I have a motor shaft with zero play. To complement the new motor, I decided to build a new battery pack using these cells. To do this, I had to cycle charge every cell to measure their capacity, which took just over a week. Entering all the values into a website called Second Life Storage will calculate which cells should be put into parallel groups, and I could then spot weld the negative of one cell to the positive of a cell from another group, until I had 6 pairs. And I had to repeat this to make a pack of 6 in series and 6 in parallel. Then I added some power wires and a balance lead to keep each cell balanced. I choose not to run a battery management system on my electric bikes, as I prefer to keep the batteries as small and simple as possible, and I use my charger to manage the cell balancing. So that's a 22 volt, 24 amp hour lithium ion battery pack, and I need another one of them to wire in series for 44 volts. But it requires a different cell layout. Here's a slow-mo video of the spot welder at 800 frames per second. It shouldn't always spark like that, as I held the contacts at an angle, which looks pretty cool, but it also destroys the welding tips. This new layout battery pack was the same 22 volts 24 amp hours, but was slightly angled to miss the frame, which when sealed in heat shrink was a very snug fit. I then 3D printed a guard that stuck out the same distance as the motor pulley to prevent my leg touching it, and this guard had holes through to the motor to help with cooling. On the other side of the frame, almost the whole motor was covered to prevent dirt and water from entering, but I kept some slots on the rear side for airflow, which seems to prevent oncoming mud from entering. The only issue is airflow carries dust, and since the manufacturer of the motor designed it for remarkable cooling performance, it also sucks up a lot of dust. So I plan to build a dust filter for the air inlet holes using some open cell foam in the future. So would I recommend you build an electric bike like mine? The 3.5 kilowatt motor performance is great, allowing it to accelerate to 30 miles an hour in a few seconds. The range is decent with about 30 miles of fun riding and even more if cruising, but if you just want performance, hub motors are the best option. This is a 3 kilowatt hub motor and it's super quiet when running a VESC 6. As well as having better acceleration. It is quite a bit heavier at 9.3 kilograms, considering my whole setup, including the battery, weighs just 7.9 kilograms, but the hub motors will fit into pretty much any bike frame, whereas mine needs a very specific design to fit. One big advantage of mine is it can be converted back to a regular bike in about a minute or two, by simply removing the battery and taking the belt off, leaving the motor and wires behind, which adds about 2.5 kilograms of weight. I know that many of you who follow my channel are engineers and most likely want to build an electric bike from scratch. And the most common question I get asked is, how do you choose a correct motor? These hobby grade brushless motors have two important specifications. The size of the motor is usually labelled as a 4-digit number. For example, this is a 6374 Turnigy motor, and I wouldn't recommend going much smaller than this for an electric bike. The second specification, and probably the most important, is the kV rating, which isn't a measurement of kilovolts, but instead the velocity constant. And it essentially relates to how fast the motor will spin, depending on the voltage of battery that you have. For example, powering this 149 kV motor with a 50 volt battery will rotate at roughly 7,500 RPM. Ideally for this size of motor, you want to be within 100 to 200 kV for an electric bike. The next thing to calculate is the motor to wheel ratio. Whether you choose to use a belt, chain or geared system, there needs to be a ratio between the two. Throughout all my e-bike developments, I've realised one golden rule to getting this right, and that's this calculation. The kV rating multiplied by the motor to wheel ratio needs to be approximately 10. For example, my first electric bike had a 149 kV motor with a 14-tooth motor pulley and 125-tooth wheel pulley, which outputs a number of 16.7, which is way too high and is the reason it lacked in torque. My version 3 e-bike had a value of 10.4, which was pretty much perfect. And my latest version has a value of 11.2, which is still fine as the motor is quite a bit larger and can handle the torque. Interestingly enough, the 3 kilowatt hub motor is 8.9 kV, which when plugged into the equation with a 1:1 ratio gives a value of 8.9. So essentially this equation converts the smaller motor RPM rating to a hub motor equivalent. So I hope this was of interest to some of you and hopefully inspire some of you to try and build your own electric bike. If you enjoyed the video, it'd be great if you could leave a thumbs up down below. If you're new to my channel and want to see other crazy projects, click subscribe down below. A massive thanks to all of my supporters over on patreon.com for making these projects possible. Thanks once again for watching, and I'll see you in the next video. Goodbye. Oh.